All right. Good morning, everyone. So I'm Dr. Christopher S. Simmons. Just call me Chris. I'm a scientist in residence at Cambridge Computer, which is kind of a non-traditional role. My role at Cambridge Computer basically falls into three duties. One is around community outreach. So I go to events like this, give you my opinion on things. Sometimes my opinions are useful. I also contribute to about a dozen open source and open science projects, including the Open HPC project, which I was one of the founders and ran the project for many years. And I also contribute to Open Storage Network and help do the user support and governance of OSN, which is an access resource available through the National Science Foundation. And I'll talk a little bit about that today. With my remaining time, it's split between, building AI and HPC supercomputers, right? And selling hardware, and most of those have NVIDIA GPUs. And we also provide sort of like a strategy Gardner McKinsey for HPC AI and research computing. And I work with, fintechs, hedge funds, biopharma, and, big national and regional HPC centers to build solutions. So you're going to hear two talks from me today. The first talk's going to be an hour and a half long, so I apologize in advance. But throughout every so often, I'll take a temperature of the room, see if there are questions, and a lot of the content builds on each other. So if you have any questions, please bring them up. Also, Zoom, I'm going to ask if there's questions in Zoom every once in a while, and we'll go from there. So originally, my first talk was titled Userspace Package Management and Reproducible Software Pipelines, and that's about a 55-minute talk. But because I have an hour and a half slot, I ended up changing it a little bit. So we are going to talk about software pipelines, but we're also going to bring data and data management into the discussion this morning. And so it's more reproducible research pipelines. And as I said, a lot of what I talk about today it's all based on fact, right? But some of it is opinion based on my career. So I want to give you a little background on who I am and where I came from, so you can use that knowledge to help ascertain whether you should listen to me or not. So my PhD is in computational quantum mechanics from the University of Texas at Austin. I started my PhD in '97, and I was the first class of NSF graduate fellows that got to use HPC for their PhD. When I finished my PhD, I was much more interested in how I solved the problem than the problem I solved. That is, I was more, my advisor called me a computer scientist, but later we actually call what I did computational science these days. And so I stayed on at UT Austin in the Institute for Computational Engineering Sciences as sort of a hired gun. So unfortunately, that center acronymizes to ISIS. And so eventually it was changed. It's now called the Odin Institute, right? Had to change it for PR reasons. And the Odin Institute is kind of like the research branch of TAC, the Texas Advanced Computing Center, where Zhao came from before coming to UW. And there I had a research group, and we kind of worked on every problem. We would partner with different research groups and take their codes, scale them out, run them on the biggest HPC systems, and help facilitate science. And around 2012, I was doing work in large-scale CFD and turbulence modeling, and we were running this 8K cube DNS simulation, direct numerical simulation of Navier-Stokes. And it was going to be a 100 million CPU hour job on Mira, which was a Blue Gene system at Argonne. And so that single calculation is going to take an entire year to run and resume, and we're only going to be able to run it once. So on the year leading up to that, we started really thinking about how do we verify our software? How do we understand its correctness? And over time, I came to a realization that, batch HPC and research computing in the National Science Foundation space started in the mid-late 90s. And today, we still kind of do things the same exact way as we do then. Best practices have changed a little bit. The pedagogy has gotten more mature to bring people up to speed, but we're still kind of doing the things the same way we did when I started my PhD almost 30 years ago. Well, between the time I started my PhD in 2012, much less now, there's this whole public cloud thing, right? And AWS and containerized microservices and scaling out servers. So what I started doing was taking the concepts of cloud native computing and bringing them to batch HPC in order to increase reproducibility and reliability. Around 2017, 2018, I, kind of got tired of just being a faculty member, and I was doing really cool stuff in terms of building systems and doing declarative, stateless, native, container native HPC. So I left UT Austin and took over research computing at UT Dallas, and I was also faculty in CS, chemistry, and math. And there I built cloud resources, or a research cloud for the state of Texas, to complement what TAC was doing, and also developed a workforce program where I was teaching postdocs cloud native concepts. I took domain-specific postdocs in chemistry, biology, and applied math and taught them some of the concepts we're going to talk about today, like containerization, DevOps, automation. And they basically sort of were the guinea pigs for a lot of the stuff I'm going to talk about today. After being at UT Dallas for about 5 years, in 2022, I joined MIT. And I was the deputy executive director of the Massachusetts Green High Performance Computing Center. MGHPCC is the supercomputing center for MIT, Harvard, BU, Northeastern, UMass system, and now Yale. And there, in addition to running the data center, I helped run and do the governance for some Ceph-based, data center-wide storage services. Got up a little bit over 100 petabytes for that. We had a tape backup system, which is about to hit an exabyte of storage that's accessible via Globus. And we built OpenStack VMs and OpenShift containerized services for research computing. And then last year, I turned 50, had a midlife crisis, and instead of buying a convertible, I joined Cambridge Computer. So here I am today to talk to you about reproducible research pipelines. So let's talk a little bit about scientific workloads in the abstract, right? When we're conducting research, it's going to be comprised of many different components. Right? The software you develop, and it should be version controlled. Hopefully it's version controlled. If it's not version control, reevaluate your life. And these days, version control means Git. I'm personally not a huge fan of Git, and I think Git is heavy-handed for 95% of the projects, but Linus wrote it, so it's cool, and Git won, right? And Git won because of GitHub. I do think it's funny that a distributed version control system only became popular once there was a centralized resource. But that's a pedantic discussion for another day, or over beers tonight if you come to the happy hour. So the software you develop should be version controlled. And almost everyone today also consumes third-party software, right? When I started my PhD, I worked on a code which is called C4. You might be familiar with it. It's an open source competitor to Gaussian. Well, Gaussian's a competitor to C4. I'm just kidding. But, it's a Fortran 77 and Fortran 90 code. It's 1.5 million lines of source. And all we needed was a compiler, an MPI stack, and BLAS libraries, right? And LAPACK. Well, these days, we tend to not write everything from scratch. We aggregate a lot of disparate components. And instead of writing software from scratch, we tend to stitch things together. Right? And when you sort of stitch these things together, your workflows become pretty delicate. And so a lot of the concepts I'm going to talk today help alleviate a lot of the issues that you come across with. All right. In addition to software you consume, there's data you acquire or you consume. And so about 55 minutes is going to be on software. The last 30 some odd minutes is going to be data. Lastly, you tie these all together with workflows. Right? Workflows, most people just work with Slurm, right? And you just have all these, slurm.sh, batch scripts that you create. But if you're developing a workload from scratch today, I would recommend using a workflow tool, right? Like SnakeMake or Nextflow. And what these do, they allow you to declaratively specify your workflow as a DAG, a direct-to-case acyclic graph, right? Which basically allows you to tie steps together. More importantly, you write these workflows in a workflow system agnostic way so that at runtime, you say I'm running on Slurm, or I'm running on PBS, or I'm running on Kubernetes, or I'm running on other cloud things. So if you're creating a new workflow from scratch, don't just write a batch.sh script. Take the time to learn a workflow tool because that gives you portability. And a lot of what we're going to talk about today is portability around software and data, but portability of your workflow is important. And of course, I have separate talks all about that. All right. So in academia, we typically run AI workloads on batch HPC systems, right? And that's fine for where most people are in the AI phase. Tuning, training, RAG with scientific data, or just playing with things. But at some point, when you want to do production, AI ML or production inference, you probably don't want to do it on a batch HPC system, right? You don't want to have to spin up an API endpoint through a scheduler, right? Or often you're working on inference for things that have real-time needs, right? Which means there's a quality of service issue. So almost every R1 just has a batch HPC system, but as a community, we probably need to do a little bit better and bring other resources into the mix. All right, so my thesis statement is that bringing cloud-native, declarative, and stateless concepts to batch HPC workloads solves most problems. All right, so let's break that down. Interactive HPC workloads are inherently stateful. And what do I mean by stateful? Well, stateful is contrasted with stateless, right? Stateless means there's no state. It's a blank slate. It's a tabula rasa. It's an etch-a-sketch that you clear and start from scratch every single time. Stateful means you're starting from some base, and then you're doing things on top of it. And that base is constantly changing, and that base, you as users don't necessarily have access to change, right? So let's say you're developing traditional C code, right? And you're compiling against a library that's in lib64, that's system-wide. Well, the next time the sysadmins do an update, that version might change, that version might update. And unless you're tracking every time it's run against every version of shared library that you linked against, your workflow by definition is not reproducible, right? Because you don't know the state of the system. Furthermore, when you submit a job to Slurm, you do it interactively in your shell. Well, your shell has been active for a minute, an hour, a day, a year, if you use Screen or Tmux or something like that. And every time you've changed an environmental variable, you've changed the state of your shell. Then you run that job. Well, what's the environment of that job? I don't know, right? HPC workloads are inherently stateful when run interactively in the way you do it. Capturing the state of an HPC system and able to freeze it and run it is almost impossible. All right. So I'm going to introduce you to some cloud native concepts and paradigms that help us programmatically express our full computational environment. And then I'm going to show you how to run it so that you always run it in a stateless way so that it has to rebuild the states in order to run the calculation every single time. All right. Declarative approaches provide better portability and are less fragile than procedural, right? Procedural is turn this crank, change that, move this. Declarative specifies the goal, right? So the way I explain it to my kids is, we have an Alexa, which controls our TV, and Alexa, turn up the volume. That's stateful, right? If it's at a 4, it goes to a 5. If it's at a 7, it goes to 8, right? It's stateful and it's procedural. But if I say, Alexa, set the volume 7, that's declarative, right? Those are the two concepts we're going to be talking about today. So treating every system as stateless ensures portability, not only in terms of software and libraries, but also in terms of data, and we'll talk about that. So the two major concepts we're going to cover in this morning session is managing software interactively with tools such as Conda and or pip probably isn't sufficient. So we're going to talk about declarative and reproducible approaches. Simply leaving your data on a POSIX file system for your AI workloads and your data science workloads also probably isn't sufficient. And we'll talk more about why in a little bit. All right, so let's talk a little bit about cloud native concepts and the history of cloud computing. So one of the typical ways that the pedagogy is developed in terms of how these tools work is the concept of pets versus cattle. So when IT started out, and I started out as an IT member, every single server was a pet. It was someone you cared and fed for and loved. You gave them names. They each had their own idiosyncrasies. They all have their own history of when they were patched and what software is involved in it, right? My servers were named after characters from Frank Zappa songs, right? And so they each had their own personality and they had their own thing. Well, if you think about that compared to the cattle industry, those are managed as a group. The cows don't have names, they have numbers. A cowboy rounds them up all together. They're all put in a corral together. They're all fed at the same time. They're all walked at the same time. Pets are beautiful, unique flowers that you interact with directly, and they all have their own personality. Cattle go moo, right? And so most of your workflows today are pets. And my goal is to teach you to create cattle workflows. All right. So all the concepts we're talking about today go back to the concept of splat ops. And when I say splat, I mean asterisk, star, wildcard, right? So DevOps was the first concept to come along, which is part of that transition from pets to cattle. DevOps is the concept of treating your operations, the management of your systems, as software development processes. Programmatically, version controlled, automatic deployment, testing, right? Those concepts. And so dev, software development based operations. All right. Now, when you take the concepts of DevOps and bring them to other domains, the marketing people did something stupid. They took the part that didn't matter, the ops, and left out the part that did is dev. So now it's called GitOps or data ops or ML ops. But it's really treating your data as a software development process. It should be dev data. It should be dev ML, but that doesn't sound as good. So just a little bit of history. Now, those concepts are good for building your servers. They're also good concepts for building your software. Well, when working with data, we need some other ways of moving data around. And a lot of the concepts I talk about today are in terms of performance and portability. And software portability is a solved problem, right? Most people aren't doing it properly and most people aren't doing it well, but we know how to do it and we'll cover that today. Data portability is another issue. And especially most of you folks just probably leave your data on a POSIX file system behind a VPN, behind an SSH session, behind a 2FA, right? And then you have to interact with it either at the command line or move it in through SFTP, SCP, or Globus, or things like that, right? Well, one really powerful tool and approach is the concept of object storage and the S3 API. And this was pioneered by AWS. And what it is, it's basically a data endpoint. It's a publicly routed service that's run over HTTPS, which means it looks like a web server to your firewall or to your network. So anywhere you are in the world, if you can access the web, you can access your S3 storage, right? So that right there is a powerful paradigm. Second, it sits outside institutional IAM borders. What do I mean by that? Well, most science projects these days are multi-institutional, right? You're working with PIs all over. And in order to collaborate on data, what are your options? Well, you can all decide all the faculty and all the students around the world are going to work on UW resources. They all get UW accounts. They all get VPN access. And you start collaborating on POSIX storage. No one does that. They do shadow IT, Google Drive, Dropbox, OneDrive, right? And so Object Store is a way, so they use that type of authentication. Well, S3, instead of using username and passwords, use API keys, which are two alphanumeric strings, right? Called your access key and your secret key, which are really just nothing more than a username and a password, but I digress. Now, to use S3 and the S3 API, you don't have to use AWS. AWS is expensive, right? You don't go to the cloud to save money, right? S3 storage at AWS, the standard tier is like $280 per terabyte year, right? Dropbox is like $100 per terabyte year, right? To give you an idea of how much it costs. Now, as I said earlier, I work in this project called OSN, the Open Storage Network, and it is provided as a service to the National Science Foundation, and you can also buy into OSN. So just a quick plug, the Open Storage Network is a national resource for sharing open science data. It's managed by the Massachusetts Green HPC Center, and it's a joint effort with SDSC, NCSA, Hopkins, and RINC. Any nonprofit educational institute or government lab can purchase a storage pod. It's $120K for the software, for the hardware. You rack it and stack it and put it in your data center. And then you send MGH PCC $10,000 a year. In exchange, you get 1.2 petabytes of object store that we run for you as a service. And then there's a cold front portal where you can log in, add users, create buckets, get access to API keys, and it's self-service on-prem object store as a service. And using this model, we just deployed, I think, our 50th petabyte of storage across the nation. We're in 23 different institutions in 18 different data centers. But if you're already an NSF Access user, right? How many in here use Access? We have some Access users in here? Couple. All right. Well, if you've ever had an NSF grant or you want to, you can go to Access and get it. And any NSF funded user can get 50 terabytes for free on the OSN today for your project. So that's the Open Storage Network. All right. Further justification for cloud native concepts. The funding crisis, right? The National Science Foundation has been crucial in funding and shaping computing research since the 50s, right? And it really started to change in 1991, the High Performance Computing Act. It sort of laid the foundation for the NRENs, right? And several of the national HPC centers, including SDSC, NCSA, and Pittsburgh. TAC didn't come along until more like the aughts. Incidentally, this is also the same act where Al Gore credits himself for creating the internet, right? This was the funding that did it. Now, even though the funding crisis looks really bad right now, and it has been really bad the last couple of months, if you look at a historical analysis of the funding trends, it's actually been in decline since 2010. Furthermore, servers are a lot more expensive now, right? In 2010, a rack of equipment was $150,000 and was about 15, 16 kilowatts of power. Now a single server is $400,000 and 15 kilowatts of power, right? Those big, Blackwell B200 DGX boxes, right? And so not only has the hardware got more expensive, but the way people are able to use this for massively scale out has increased the hardware resources. So even with the latest spending debacle, right, funding debacle, it's still been going down over the last years. And relying primarily on federal funding presents several critical challenges. First, without being political, shifting funding priorities, right? Things are always changing. And even, again, even irrespective of the last couple of months, there's been these constant shifting funding priorities at the National Science Foundation. If you've sort of plugged in and pay attention to what all the funding is, you'll notice there's always a competition between the computer scientists and the computational scientists, right? And they kind of go and fight with each other. And when the computational scientists are in charge, you get big systems, big national data facilities, big AI systems. When the computer scientists are in charge, you get funding to develop yet another domain-specific language, right? They're both important, right? And they both complement each other, but there's always politics when you look at money. Securing long-term funding from federal government is tough also, right? It's feast or famine. You get a grant now, you're fantastic for the next 3 or 5 years. You're eating good, but you might not get another one for several grant cycles. The peer review process is not perfect. And a lot of people get in this treadmill of chasing the reviewer. And it's what I see a lot of my students do when they first graduate and start writing proposals, is they submit a proposal they're really happy with, and they get feedback from the reviewers. And then they start chasing what the reviewers say, but the next batch of reviewers give them some totally different recommendations. So it's fine to tweak your proposal, but you have to realize not every peer is equal. Not all peers are equal. Let's just say it like that. Furthermore, if you look at the historical funding across the NSF and NIH, there's a preference for large and well-resourced institutions, right? At the end of the day, there's an NSF program manager who's responsible for that project. And when there's a big project or a new PM, they tend to fund the MITs and Harvards and not the University of Northeastern Iowa, right? Or the Southwestern Louisiana, the directional schools, right? Which are important for our education, right? They develop the bulk of our workforce, but they're not nearly as well funded. Lastly, it's really hard to get operational costs and boring stuff funded. I need money to expand my network. I need money to expand my storage. Most of the funding goes for novel, slightly new, but not too much far field from what you're doing now, right? The mundane stuff they don't fund, and the really cool, high risk, high reward stuff they don't fund, right? It's the slow progress they tend to fund. All right, so what are possible solutions? Well, one is to take advantage of economies of scales with consortium and shared infrastructure, right? I've worked at a lot of such organizations. And then there's also private-public partnerships and philanthropy and private foundations. And as an aside, some colleagues and I submitted a paper to PERC that got accepted that sort of analyzes the funding crisis and proposes some community next steps on how we can work together to try to create these programs. And wearing my commercial hat, I'm currently working on creating some internship programs that help do matchmaking between EDU and industry. Well, why does industry care about funding workforce development? Well, the majority of R1s provide only batch HPC systems with no emphasis on cloud-native concepts, and the real world runs on Kubernetes, uses automation, uses DevOps, uses CI/CD, and we are supposed to be preparing our national workforce. So bringing an actual cloud-native system improves your story, but bringing cloud-native concepts gives you an edge. Historically, there have been programs that help fund this, and I'm a huge fan of the CC Star program. I've worked on about a dozen funded CC Star projects. I hope the program comes back. If you want to get access to some resources today to play with some of these concepts on cloud-native resources, instead of taking these concepts and bringing them to your batch HPC systems, there are national resources which can help you today. We talked about the Open Storage Network as one option that provides S3 storage as a service. There's the NRP, the National Research Platform, which is, again, out of San Diego, and they have a system called Nautilus, which uses a similar model to OSN. That is, you buy the hardware, you put it in your data center, the NRP and Nautilus teams sets it up, installs Kubernetes, and runs it for you. In exchange, you donate a portion of that capacity to the nation, and then you run your workloads on top of that. Nautilus is what they refer to as potluck computing, right? You kind of bring what you have. I also like the analogy stone supercomputing, if you remember the stone soup parable, but very powerful resource. And then lastly, there's Jetstream 2, which is a joint effort between Indiana and TAC, and I believe there's another Arizona State, one of those universities, where they have a big OpenStack cluster, which is virtual machines for science, right? Where you can spin up your own virtual machines. All right, so I'll take a break right there. Any questions before we continue? Anything in Zoom? All right. So, as I said, the title of my talk was around user space package management. So what does that mean? Let's parse that. Package management refers to the process of installing, updating, configuring software, right? And this process is handled by tools known as package managers. Package managers can be provided by the operating system, the App Store on Macs, right? The Windows, what is it called? I don't use Windows. Windows App Store, or whatever it is. If you're a Linux Andy, right, there's things like, apt and DNF and Yum, or Pacman if you're an Arch person, right? Gentoo if you like to compile things from source but never actually do any work, right? There's all kinds of different package managers at the OS level, but there's also language-specific and third-party package managers. Now, Userspace means a user can run the package manager without escalated privileges, without root privileges, right? And it's contrasted with kernel space. All right, so As I said, hopefully you already version control your software in Git or GitHub. But more than software development can be tracked. I track all my dot files, right? My dot files are tracked and synchronized across all my systems. I track my Slurm submission scripts. I track my files which build software stacks, which is what we're going to talk about today. I version control almost everything. In the real world, I'm a mess. Digitally, I'm really organized, right? All right. So as we said, the vast majority of scientific workflows consume third-party software. So how best to manage software stacks? Well, almost everyone in here started with the first way, which was let someone else do it. And when I was growing up, and going through HPC systems, that's the way most of them worked, because most of the software we used on these batch HPC systems were open source simulation software, your GROMACs, your Ambers, your VASPs, your C4s, your OpenPhones, right? Your WRFs, right? Those type of software, and they don't change very rapidly. They're complicated to compile and set up. They're more complicated to integrate with an MPI stack that integrates with your scheduler. And almost all HPC centers provide some way of providing access to this type of software. It's usually a module-based system. How many people have used modules? Module load compiler, module load MPI stack, module load boost, Trilinos, FFTW, right? Those kind of things. Well, and that works really well up until it doesn't. On top of that, people are using more scripting languages like Python. How many Python users? R users? Julia users? Julia, yes, Julia is an amazing language. We should have more Julia users in the world. Come talk to me sometime and I'll tell you how Julia is amazing and will solve most of your problems. All those sort of scripting languages or interpreted languages, if I don't want to be so dismissive, these interpreted languages are much easier to write software for. It's much easier to release software. I would argue it's almost too easy to release Python software because as scientists, we suck at writing software, right? The Python software ecosystem's a mess. And managing Python at a system level is almost impossible because they change constantly. The packages break compatibility, backward compatibility, API, ABI, and you don't want to manage an infinite number of versions, right? Since I started talking today, the TensorFlow and PyTorch API changed probably twice each, right? They're constantly changing. So we can no longer find someone else to do it. Well, at least we can no longer find a systems administrator or someone centrally to do it. The next step people do is they find a student to do it. And there's a student in the lab who maintains all the software. And that's great until the student leaves. Now, the student doesn't usually leave until year 7 or 8, right? Because they are also managing the IT. And as an aside, those are the students I hire. Those are the best students. The more you know about IT and Unix, the better you're going to be as a computational scientist. Okay, so we need to be able to manage our own software. So we can either now manually compile from source, and for some things that's fine, but for the majority of things you don't want to do that. So we're going to talk about using Userspace package managers, and you can use these and interactively configure your environment, or you can programmatically drive these. So we're going to look at 3 approaches. The Conda ecosystem, I'm going to briefly mention SPAC, and then we're going to talk about containerization. All right. So the approaches we're going to talk about today in terms of managing software are all built upon a text-based declarative configuration file. And as soon as you hear text-based, the first thing you should think is version control, right? Because that gives us a change log, an auditability, a way to roll back, right? A way to collaborate, a way to exchange, a way to redeploy on different systems. And so this GitOps approach is an operational framework or a paradigm where Git is the single source of truth. It manages your infrastructure, it manages your application deployments, it can manage your data, it can manage your workflows, and it can also launch your jobs. And that's how I make all my students work. So key principles of GitOps. Git is the single source of truth. If it's not in Git, it doesn't exist. Use declarative tools. Declarative tools are much more robust. Automate your workflows and your software so that when you check something in, it gets tested. Deployments are immutable. Every time you pull something down and run a job, if it fails and you need to tweak a solver tolerance or you need to change an input file, change it locally, check it into Git, check it out from Git, run it. Never change locally and run because you're no longer capturing the state of your workloads. All right, Conda. How many people use Conda? Yeah. Conda is an open source package and environmental variable for multiple program languages. Python, R, Julia, Lua, Ruby, Fortran, bunch of languages. Anaconda is a distribution of Conda. It's a data science platform which comes with a GUI and 300 packages and some licensing burdens. Don't use Anaconda. I'm just going to say it. Don't use Anaconda. It has some licensing changes recently that make it kind of annoying to work with. On top of that, if you want to use Anaconda, use it on your local machine. But don't put Anaconda on an HPC system. Because when you instantiate Anaconda, you're instantiating 300 plus Python packages, which sources thousands of small files, which DDoSes the metadata server for your parallel file system and will take it down. So don't use Anaconda. So what can you do? Well, you can start with Miniconda, which is a minimal Conda environment. It doesn't come with user packages, just enough stuff to start installing things. But again, it requires Python, and the native Conda driver and dependency resolution is painfully slow. I don't think I could write it slower if I tried. However, there's things like Mamba. Mamba is a re-implementation of the package dependency resolver in C++, but there's also Micro Mamba, and Micro Mamba is what I use. Micro Mamba is a single executable. It's a statically linked version of Mamba that has no Python requirements, has nothing installed by default, and is made for these containerized, stateless, portable workflows. All right. So using Conda or Mamba, however you want to do it, you can create isolated environments. And so one of the next thing that I see people have problems with Conda is first they work interactively and they don't use environments. They put everything into the base environment. And if you know anything about Python, you're going to need lots of packages. All the packages have dependencies. And sometimes the package dependencies of two different packages require the same other package with different versions, right? Also, people mix Conda and pip willy-nilly. That's a technical term. And it's very easy over time to create these interactive Conda environments or base installs that you cannot recreate at this point in time because of history and versions and the way things changed and dependency resolutions over time. So use environments. Environments allow you to create isolated Python installations that could be workflow specific, it could be tool specific, however you want to do it, right? And there are two ways of creating a Conda environment: manual specification interactively, or a config file that you check into Git. And it uses YAML. YAML stands for YAML ain't markup language. It's not yet another markup language. It's actually not markup language. It's a serialization standard. Okay, so let's compare Conda and Micro Mamba. Conda is implemented in Python. Micro Mamba is C++, is a static link standalone binary. Conda requires a full Python stack. Micro Mamba is just a binary. Conda is slower, is kind of nice. It's single-threaded. Micro Mamba uses this libsolve, which was written by the Mamba folks, and it's multi-threaded. Conda is mature. It has some features that Micro Mamba doesn't have, but the features that Micro Mamba doesn't have, I don't think you should use anyway. because it goes against sort of the paradigm that we're talking about today in terms of this declarative portable environment. All right, installation is real simple, right? You literally just tell it your shell, you hit an MPI, you hit a URL with curl, and that'll install the binary, right? You get the binary set up, you install your environment. From there, it shoves some things into your bash RC or your TSHRC or your ZSHRC if you're one of the cool kids, right? If you use Z shell, you then log in and that activates it, but nothing gets instantiated right away. You have to activate your environment, and then you install packages, right? In this first example here, I'm installing Python 3.11, and I'm not specifying an environment. Is my cursor showing up there? Yeah, okay. And that'll install it into my base environment. If I wanted to create an environment, here's an example of how I'd create a NumPy environment. With Micromamba, create my environment and then NumPy. All right. So here's an example where I've created this NumPy environment or NumPy in my environment called my env. And so here I am on your HPC system login nodes. I log in, which Python has nothing in my path. I activate my env. I now have Python. When I set it up, I didn't specify any Python versions. I just said NumPy. So it'll get the most recent version of Python, which as of 2 nights ago was 3.13.3. All right. And then I deactivate my environment and that cleans it up, right? It's no longer in my path. Now, activate, interact, and deactivate is how you do it interactively. But if you want to script something, you're not going to be able to activate and then run a command because you're not in an interactive session, right? So you use the separate syntax here, this Micromamba run. I'm running this which Python command against my env, right? And that's how you put environments into a Slurm script and run with that, all right? And then here's an example of what all got installed. So when I just installed NumPy into my env, it pulled in all these dependencies. So here you see NumPy, the blue one that's highlighted. That means that is what I explicitly installed. Everything else is a dependency. You'll see some libraries, you'll see BLAS, you'll see Python, it needs Python, OpenSSL, right, for secure communication with, secure sockets. TZ data, time zone data, right? It needs to know time zone, right, in order to run a language, etc. All right. What if I didn't want to use the latest version of Python? What if I wanted to use an older version of Python? Well, that's fine as well, right? So as I said, by default, when I just installed NumPy, it gave me 3133. Well, here, let's create an environment called Py12, and I'll ask for Python 3.12. Because I didn't ask for a micro release, right, major, minor, micro, I asked for 3.12, it'll install the most recent version of 3.12, which is 3.12.10. Cool. All right. Now, if I take that environment, my env, where I installed NumPy, I can write out a YAML file with all the packages needed to regenerate that environment. But when you do that, notice it hard codes the versions. Okay, so every time I run a job, I do generate one of these with the versions, and I save it along with the job script, so I know exactly what versions were run. But when I build my software stacks, I don't hard code the software versions, right? So, and we'll talk a little about that in a bit. So YAML, as I said, ain't markup language. It uses indentation and a minimal syntax to represent hierarchies. The structure is indentation-based with spaces, not tabs. Tabs will leave you down a path to pain in these YAML files. It's spaces. There's no curly braces or square brackets like JSON or XML. And it's just spaces and nesting, which defines the structure. And there are 3 basic data types. They're scalars, which are simple values. There's sequences, which are lists indicated by hyphens. And then there's key value pairs or mappings, which are separated by a colon. So let's look at an example. So here's an example of a YAML file. Name colon joke. So the name of my environment is joke, right? And that is that key value pair. Channels, I've started a list, but right now I only have the defaults. But you could add channels that are NVIDIA specific or Intel specific or other projects which publish their own Conda repositories. That's how you add extra software repositories, is under these channels. So the dependencies, colon, key value, the key is dependencies, the value is a list, right? Hyphen as the list. I'm going to install Python 3.9. I didn't specify a micro, so it'll give me the latest micro version of the 3 minor 9. It's going to install pip, and then it's going to use pip to install PyJokes. All right. So I then run micromamba env create -- file, and then micromamba activate joke. And I ran PyJoke 3 times, and I got some very clever old jokes. I changed my password to beef stew, but the computer told me it wasn't stroganoff. Right. I didn't say they'd be funny. So that's how you work with environments. What are the best practices? When starting a new environment, always generate it from an environmental file rather than the command line. Maintain your files in Git alongside the code repo and the science for the project, right? Your source code goes in there. Your files for your package manager, which install the dependencies, is there. Your workflow is there. Your Slurm scripts are there. Everything needed to do your science lives in Git. As you add packages to the environment, do not install them locally. Check out your environmental file, update it, check it into Git, pull it down, recreate the environment. Unless you must, try avoid specifying the versions of each package. That way, every time you run and update the package or update your install, you get the latest versions. And as one API changes or certain features break, you hit them one at a time instead of defending your PhD 6 years later and everything doesn't work with new versions, right? You have to use specific old versions, right? Keep your software fresh and up to date. Mixing Conda and pip can cause issues, but sometimes it's unavoidable. Not everything that's in Conda is in pip. Not everything that's in pip is in Conda. There's much more stuff that's in Conda than pip. So my recommendation is try to use Conda first. And if it's not in Conda, then hit PyPy or pip. All right. Any questions about Conda? Micromamba, any of these concepts? All right. Now, Conda started more on the interpreted languages and eventually added, Fortran and C and libraries, mostly for those interpreted languages to link against, libgc, right, or libblaws or whatever. SPAC is like Conda, but it's developed, for compiled languages as a first-class citizen. C, C++, Fortran, right? It was developed out of the DOE Trilabs, right, to be their package manager for performance portability. It's much harder to use than Conda, but it allows you to do these really cool variants where you can say, basically have not only versioning, but variants that combine certain MPI stacks, certain libraries, certain GPU accelerated libraries, and is much easier for building robust, customizable, portable, performant infrastructures. So SPAC works a lot like Conda. You install SPAC via git clone. Actually, you just pull SPAC down via git, and that's how you install it, because SPAC is just Python. You find and install packages. You create environments. Here with SPAC, sometimes you create your own MPI stacks, or you integrate with the system-wide MPI stacks, and then you version control your file. SPAC has a steep learning curve, but it's extremely powerful. And so if you're doing scale out, really high performance, either accelerated or CPU-based and compiled languages, then it might be worth your time to learn spec. All right, containers. Software containers are these lightweight, portable units that package not only your software, your application, but also all the libraries into a runtime environment. Basically, you're running an entire operating system minus the kernel as a single binary on your system, on your bare metal system. And your application that runs inside there, it doesn't see the system-wide lib64. It doesn't see the system-wide user include. It only sees what's in the container, right? And that allows you to have this reproducibility where you control what your software links against, even though it thinks it's linking against the system, right? One of the big problems when you're working with compiled software is outwitting the build system. Right? If you ever worked with someone who has a highly customized makefile or some M4 macros or a bunch of CMake nonsense, right? Sometimes they try to make it easy for you by using system libraries, but sometimes you don't want to use system libraries. And you get in this game of trying to outwit the build system. Well, that's a path to nowhere and pain, right? Containers solve that problem. Some example container runtimes. So Docker was the first kid on the block. And Docker these days, you wouldn't use it on an HPC system, and we can talk about why in a little bit. But Docker is great if you want to run containers on your Windows or Mac system, right? Docker desktop, you can pull down from the internet, and you run it on your Windows or Mac, but it actually runs the containers on a Linux virtual machine that Docker desktop manages for you, right? Now, Docker on a Windows machine will allow you to use an NVIDIA GPU. Docker on a Silicon Mac, right? You're not going to use accelerated computing. It doesn't support running on Apple Silicon, even if the underlying software does, because the Mac OS virtualization layer doesn't do a good job exposing that. Docker is what's used a lot in production, along with Kubernetes for like web services. But if you like this Docker concept and this way to spin up services, the proper way to do it is with Podman. So Podman is a complete rewrite of Docker. It's open source. And it uses the same exact syntax as Docker, but it runs all in Userspace. Now, Podman only runs on Linux, though. And then lastly, there's high-performance containers, or HPC containers. And Singularity was the original one that, again, grew out of the DOE labs. The Singularity project had a schism, and there's now Singularity. There's Singularity CE, the community edition. And then there's Apptainer. Apptainer is the one that's installed on your HPC systems. The way you use Singularity and Apptainer are exactly the same. All right. So some key terms. Containers build images. And images are unchanging static files that hold all the executable code that's isolated from the underlying bare metal IT infrastructure in terms of what the software sees. A registry is like GitHub for images, right? So Docker Hub, right? Quay.io, NVIDIA has one. There's a registry built into GitLab, right? And this is where you share images or store images. All right. And containers avoids the works on my machine issue and allows you to share your exact environment via images. So Docker, use on your local machine for developing and prototyping. By default, Docker requires root access on the host. You can add users to the Docker group so they can run without explicitly having root privileges, but in the container, they're running at root. And if you're smart, you know how to exploit that. So don't run Docker on your multi-user systems. Apptainer, production workloads, no root privileges required, and it's built for scalability in terms of running these big parallel calculations by design. Podman provides a rootless Docker, but the Podman runtime is Linux only. It also supports some orchestration kind of like Kubernetes or Docker Compose. And it's great for running along sort of web services on your HPC jobs, right? SQL is still useful, right? And so a good use of Podman is when you're spinning up your HPC jobs, you can actually use Podman to spin up an SQL database for the period of that job and query against that, or Redis, or you can look at some of these Tensor dashboards for looking at training, right? And those kind of things. All right. So I'm not going to spend a ton of time on building containers because there's a really great tutorial on y'all's website on Hayek. So I recommend you do it. But the concepts apply from Conda to containers because they're all based on the concept of GitOps. Work with your Docker file. Docker files are the way you build Docker containers. However, from a Docker file, you can also build Podman and Apptainer containers. They read the same syntax. And the internet is full of Docker examples to start from, as opposed to Singularity examples. And most people just edit Docker files. They don't create them from scratch. Each instruction in the Docker file specifies a step in the process of creating an image. And it happens as a series of overlays. And then when the image finally gets built, it gets compacted into a single image. It provides a reproducible way to define the contents and the behavior of the image. So you can use a Dockerfile to set up basically your own Userspace operating system and install software. You can also use Docker files that automatically ingest your Conda environment files. Or you can use SPAC to build containers directly. Multiple ways to build containers. All right. Any questions about managing software? Part 2 of my talk, data management, right? So perfect segue. Is that Alex from our team? Was that a plant? No, that's a perfect question. That's exactly what we're talking about next. Data management for AI workloads is extremely important, and most people do a really bad job of it, right? So as I said, I'm a quantum chemist by training, right? Computational chemist. And I've mostly worked in physics-based simulations, right? And so when I'm working with physics-based simulations, I have some physical intuition, right? I know if a temperature is negative in Kelvin, something's wrong. If I know, right, I'm getting a shock when I'm not supposed to in a flow, or I know I'm getting discontinuities or numerical errors, right? I have physical intuition to what the correct answer should be, right? In AI, it's data fitting, right? I mean, it's powerful data fitting, but it's interpolation, it's data fitting, right? LLMs are just word calculators, right? Everything is just a mathematical function that's trained on data. So there's no physics. Everything comes from the data. So if your data doesn't have proper hygiene and cleaning and provenance and reproducibility and traceability, then how do you build confidence in your AI, right? So, in past parts of my life, I used to work in, IT support, right? Or facilitation, right? Science support. And, so many times people would submit a ticket and say, I don't know, my LAMPS workflow no longer runs. Can you look at my input file? You look at your input file, and at the very end, you see a :WQ, right? They were using Vim and they tried to escape and they were in insert mode, right? Instead of command mode, and they put a little turd in their file and it no longer works, right? Now think about this. Everything that trains your AI model is in the data. It comes from the data. And if that data just sits on that POSIX file system, how do you know it hasn't been changed? You don't, right? So let's talk about fixing that. All right. So one way is the GitOps approach that we talked a little bit about. And when working with the GitOps approach, you can store your data directly in Git. But that only works up to a certain size, right? Storing all your data directly in Git is a path to pain for large files. And large is not that big, right? And you start carrying around, right, these Git repos that you check out is every version of every file over the history of that Git repo, right? And binary files don't get stored as these really small diffs, right? And so it grows. So Store your data in Git if it's a CSV file and it's a couple thousand entries, right? That's fine, right? But if it's binary data or HDF5 files or any type of data files, don't store them directly in Git. So if you want to stick with the GitOps approach and use Git as your single interface to the world, there's a plugin or an extension for Git called Git LFS, where LFS stands for large file storage. Git LFS, basically, when you add a file to LFS, it basically adds it to a dot file, kind of like git ignore. But instead of ignoring the file, it says when I merge, push, check out, check in, instead of sending the file in Git LFS that's managed by Git LFS, instead of sending it directly to the Git repo, send it somewhere else, right? Somewhere else is built directly into GitHub, and it's free up to 10 megabytes. After that, it's more expensive than AWS S3. GitLab supports it as well. And GitLab is an open source GitHub. You can host it on-prem. You can pay for a cloud-hosted service of GitLab. If you wanted to use Nautilus by NRP, as we talked about earlier, they have public GitLab repos you can use. And with GitLab, you can redirect your Git LFS to an S3 bucket. And you can use OSN as that S3 bucket. If you want to use Git LFS with GitHub, but send your files to OSN, you can do that as well. But you need to install a proxy. There's NPM, the Node Package Manager, JavaScript package managing service. There's something where you can spin up an NPM proxy on your local machine. And when you do Git LFS check-ins to GitHub, it'll intercept those and send them to S3, right? As opposed to sending them to Git. Right? Now, the data ops approach is what the question was about in Zoom. So data ops is a data management practice or framework that allows us to programmatically interact with data. So instead of using Git for data, we're now using additional tools which allow us to programmatically, thus trace, thus write software, thus check it into GitHub to manage our data. So key principles of data ops. We want to make collaboration really easy. We want to be able to automate our cleaning, our checking, our testing. We want to be able to monitor it. We want to have scalability, and we want to have auditability and governance. So compared to the GitOps approach, the tools of data ops are more powerful, but require more intrusive workflow or code changes. So the two tools we're going to talk about today are open source, and that should be considered. The first one is DVC, which stands for Data Version Control. And DVC is an open source version control system designed for not only managing data, but also data sets and machine learning models. It actually allows you to track machine learning experiments. And just as you would merge, fork, check in, check out software on Git, you can merge, branch, fork, check in, check out data sets, which are a view of the subset of the data, as well as your calibrated machine learning models. And you can do this prototyping and testing of your entire pipeline with using DVC. Now, DVC is serverless. That means you don't need to install a server and have something in the web running. It's just a client. It's storage agnostic, which means you can use your local storage as your backend. You can use it over SSH, SFTP, or what I do is use S3 storage. It provides reproducibility for your data. You're already tracking your code, but now you're also tracking your model. You have a model registry, and you're allowed to do your AI experiments that way. It provides ways to define and manage programmatically data pipelines. And it uses the same exact command syntax as Git. So basically, when you work with DVC, you work with it in your Git repo. So I have my project that's in GitHub. I have my source code. I have my environment.yaml files. I have my Docker files, but I don't have my data. I check out my GitHub repo to my local workstation or my shell on my HPC system, and I change to that directory. I copy a data file into that directory or some subdirectory. And instead of doing git add, I do DVC add. And when I do DVC add, it adds it to git ignore. Right? Then, if I want to work with code, it's git branch, git merge, git push, git pull. If I want to work with data or my machine learning model, it's DVC add, DVC pull, DVC get, DVC, etc. It works exactly the same syntax. Extremely powerful paradigm with modest changes. Now, working with large data sets introduces additional complexity because I'm advocating for stateless, which means I don't want software there, but it kind of implies I don't want data there as well. And up to a certain size, I say that's correct. However, if you're working with big data, for whatever big means for your case, that means you have to wait for everything to be pulled down every time you run a job. And that's not what you want to do, right? So there's two ways to do this, right? One is to cache and one is to copy. But because DVC is version controlled aware, each of your local copies are just checkouts. As long as you check things back in, you can keep your current state on your Scratch file system. And when you run your next job, you make sure you do a DVC pull, and that'll just send the deltas that have changed in the data set downstream. So that's how you manage large data sets with DVC. Conceptually make sense? Yeah, cool. LakeFS. LakeFS is open source data version control and management system that brings these versioning and Git-like capabilities to data lakes. This is not serverless. This is something you have to set up a server in the cloud or server on-prem, install software, set up an API endpoint. But it allows users to manage, track, and collaborate on large data sets. Furthermore, there's integrations with applications that allow you to programmatically interact with the data at your software level, as opposed to using an external workflow tool like DVC. So LakeFS supports versioning, branching, merging, lineage, auditability, snapshots, rollbacks. It's horizontally scalable. It integrates with commercial data lakes, but you can also use OSN, and has a web interface as well as a command line tool, right? It's called Lake Cuddle. If you've ever used Kubecuddle, like Kubernetes, it's very similar. It's Lake Cuddle. It has direct integrations with Python, R, SageMaker, Spark, right? Many such tools. And in my Python software, where I'm doing my science or my AI/ML, I can actually work with LakeFS directly. And instead of pulling the data down locally to the local file system, running my job and reading into memory, I just launch my job and run my Python code. And it runs, the software interacts with the LakeFS API and pulls the data directly from LakeFS into memory. And then when you close it, it writes it from memory to the data lake. It never hits the local file system, right? Which really eliminates that last step, what you're talking about, right? Especially if your LakeFS server is right next to you. Or you spin up your LakeFS server with Podman that's being stored on your local file system so your IT team backs it up, and then you programmatically interact with your data. This requires the most invasive changes, really requires you to change your software, not just the way you interact with software, but it's extremely powerful. All right, so I've got some information here on Open Storage Network. These slides will be provided. Information on getting started with Access, information on getting started with Nautilus and NRP, links to GitLFS, DVC, and LakeFS. More data on more information on all the tools we talked about today. And just to sort of bring this all together. So a smart person earlier today said, bringing cloud native, declarative, and stateless concepts to batch HPC workloads solves most problems. And I would say this solves most problems, but it requires you to change the way you work. So your goal is to make your workflows boring. It's to make them cattle. It's not to make them pets, right? First, tackle your software problem. Version control the software you write. Use declarative tools to install software. Version control the config files for those declarative tools. Second, get your data under control. And for me, the Goldilocks there is usually DVC. Unless it's a really small toy project, I usually skip the Git LFS and I go straight to DVC. And it's only for the really big projects with lots of people, especially if I'm working with like controlled data, PII, HIPAA, patient-specific, ITAR data, right? LakeFS gives you that auditability, that security, that CYA, right? After that, consider automation. So we talked about the concept of DevOps, right? I called SplatOps, right? GitOps, et cetera. Well, DevOps is only part of it. The other part of it is this concept called CI/CD, which is continuous integration, continuous deployment. That is, anytime I check stuff into Git, tests run, right? That could be a regression test or your test suite for your software, right? And like for certain projects that I work on, like physics solvers, we have, a couple thousand unit tests. And if someone checks something in and it breaks a unit test, it'll actually reject the commit, right? I have some projects where it doesn't allow you to commit if it breaks a test, or you're allowed to do it on a branch, but not on main, right? Those kind of things. Well, what I did when I was a faculty member, and so I still have some students at different universities that I work with, postdocs as well as graduate students. And as I said, they don't work with systems interactive. They work on their laptops or desktops and local systems. And then when they're ready, they check their workflow into GitHub. I then have, on some of my HPC systems, I have what's called a GitHub runner. GitHub runners allow you to set up triggers such that when you check things into GitHub, it'll automatically do things. And so none of my students submit jobs interactively. They check in their workflows to GitHub. It then triggers a job to run. If the job fails, they have to fix it, check it into GitHub to run it again. Right? GitHub Actions, you can do via self-host runners. For open science and open source projects, if you just want to compile software and test at the CPU level, not the GPU level, there's several CI/CD, these continuous integration, continuous deployment services that you can use for free. One is Circle CI. So you can apply to Circle CI, say you're doing open source or open science project, and they'll let you trigger GitHub builders on their infrastructure for free. So like for the Open HPC project, right? We use that to build our RPMs on check-in for distributing software, right? Lastly, there's a software called Tapis, which is developed out of TAC, which is kind of like this GitHub runner for science. It understands data. It understands versions and data pipelines, and it interacts via SSH and SSH keys. And so when I was at UT Dallas and ran research computing there, every time a system got retired at TAC, it would roll up I-35 North from Austin to Fort Worth, Texas. It would go in my data center, and my students had interactive programmatic access to 30,000 cores of CPU. But the only way you can run on those systems is through GitHub. So that's my talk. Any questions? So the question was, which projects do you recommend Mini Mamba versus containerization? So for me, I almost do everything with containerization these days, because containerization is not only the software, but it's the entire underlying operating system. And I talk a lot about cloud native concepts as well as cloud native infrastructures. And so here's my paradigm. So when I'm running an HPC system and build an HPC system, you have to build what's called a provisioner. And a provisioner is what provisions or installs the bare metal hardware. So I use a provisioner that's called Werewolf or Werewolf 4, which is by the same people who do Aptainer. They're also the Rocky Linux folks, right? CIQ is the name of the company. So Werewolf takes a container and turns it into a bootable image on bare metal. Then I take my operating system containers and I put all my software in it. So I run my operating system container on top of the same operating system on my HPC systems. And then I take that same container and I can run locally with Docker, or I can run on a Kubernetes system. And I always have the same exact environment everywhere. So to me, Micro Mamba is a point on the path to get to containerization. But the concept of images and image repos and Docker Hub and things like that are just a much more powerful paradigm than a single configuration file to install software. So for me, Micro Mamba is a walk to get to the containerization run.